Hello everyone, welcome back to Calculus 2. Today I'm going to cover chapter 10. It's all 4 sections, first 4 sections of chapter 10, and that's all we need to know for chapter 10. 10.1 all the way to 10.4. Even though it's like 4 sections, and actually we introduce you new concept, new items, so it's pretty simple and straightforward. So let me start with 10.1 and 10.2. I'll be talking about parametric equations, okay, and the calculus. 10.1 and 10.2 parametric equations. Okay, so let's explain this a little. Before, you have a function y equal to f of x, and all you can do is a curve like this is passes the vertical line, right? And what about the curve that's not passing the vertical line? Say the curve like this. It fails the vertical line test, so it's not a function y of x anymore. So we found a new way to represent a curve. Is we think of y as a function of new variable t, and then x is also another function of variable t. I will book write this way, but to be honest, I would prefer to write this way: y in terms of t, okay, and then x in terms of t. That looks shorter and easier, okay. And y is a function in terms of t, x is another function in terms of t. This is how the book write, and then you can write this way. You can later on you got z in count 3, and then what? Parametric equation in 3-dimensional space. X, y, z in terms of t. That's going to be shorter, and then you don't have to introduce new variable. And yt, think of t like time. So t equals 0, the point right here. Then what? 0. And then t equal to 1, the point moved there, right? The particles keep moving along the curve, right? Along the line. That. So for example, say if I have something like x is equal to t squared minus 2t, and then y is equal to t plus 1. You see, x is a function of t, right? So you can write this way. That's the way I mentioned, xt, and then yt. That's another function of t. All right. And if you graph this parametric equation, and you're gonna see something like this. Like parabola looks like that. Okay, of course it fails the vertical line test. So this is a more general way of representing a curve in the 2-dimensional space. And sometimes you can convert it back to a function of an equation in general of x and y. If you can solve a t, say in here what? Right, x equal to t squared minus 2t, right? In short, y equal to t plus 1. If I can solve a t from one of those 2 equations, say in here I got t is y minus 1, subtract 1 both sides. I plug the t into the first equation, then I have x equal to y minus 1 squared minus 2 times y minus 1. You see what? I have an equation in terms of x and y, no t. But many other times you cannot solve a t, then just leave it this way. Equation where x is a function in terms of t, y is another function in terms of t. And this is called parametric equations. Okay, those t is the variable. X, y. Now think of function. Okay, and this is what we have. So that's the introduction. And see, look at this. Say cosine first, right? Cosine square of t. X equal to cosine of t. Then x equal to cosine of t. Y is equal to sine of t. And guess what? Where t runs from 0 to 2 pi. You know what this is? It's going to be a circle, because you know what? X squared plus y squared is going to be equal to cosine squared plus sine squared is equal to 1. Right? And then you graph this is the circle. Radius 1. T equals 0, it's going to be right here. All the way to 2 pi, because t, now think of what the angle, right? You have the whole circle. Now, here comes something very special about the parametric equation. What if, instead of cosine t, I have equation cosine of 2t, this is sine of 2t, okay? And t still runs from 0 to 2 pi. So x squared, y squared, is cosine squared of 2t plus sine squared of 2t equal to 1. It's still circle, but you know what? It's going to be grabbing along a circle twice. See why? When t runs from 0 to 2 pi, then 2t going to run from 0 to 4 pi. So what? 0 right here, 1t, 2t, 4 pi. So really the particle keep moving along the circle like twice. Okay? Still represent a circle. All you see is really one circle, but this equation you see, you know that it's going to be two circles on top of each other. The particle start from 0t equals 0 all the way to 2t. You're going to be 2 times because the t is times 2. Okay? So pretty much this is the end of 10.1, introduction to something called the parametric equation. And all I can tell you is what all you want to know is x as a function of t and y as a function of t. And if you don't have a graphing calculator and you want to graph it, just make a table, okay? What? 3 columns, t and then x and then y, okay? Look at some value for t, 0, 1, 2, 3, and then you calculate x, calculate y, you plot the points, you have a sketch of the graph. Okay. Now, let me move on to the next section, which is, I think, there's more things to talk about. We'll talk about some calculus on parametric equation. Say now you got x as a function of t, right? Y as a function of t. So let me give you an example. I'll use the same example that we had before. We have x was what? T squared minus 2t, and y is how about t plus 1. This is a curve. Okay, it looks like this. Say you want to find the tangent line. You want to find a tangent line, you find the slope, right? Slope is going to be dy over dx. Okay? This is really people used to write y prime, but now it's not really clear if you write y prime anymore. You see what? Change of y over change of x. I'm using Leibniz notation in here. Dy over dx. Because the variable now is not x anymore, our variable is t. So I prefer to write this notation. How do you calculate dy over dx if you know x and y right here? And it's like basic algebra. Dy over dx is dy over dt. Let me write this way then. Dy over dt, then divided by dx over dt. Okay? So divide dt on top, divide by dt on the bottom. And this means what? The derivative of y times t, the derivative of x times t. Now you can do it. Dy over dt, dy over dt right here is equal to 1. Dx over dt right here is 2t minus 2, right? Because the variable is t. Now you can bring it back to normal. This is 1 and then over 2t minus 2. And that depends on the value of t. You will have dy over dx, which is the slope of the tangent line. And then you find a point, you have a slope, you have a tangent line. Okay? So this is dy over dx. Let's make this a little bit more complicated. Let's move on to the second derivative. And then before we write this way, y double prime, right? It's really what? The derivative of dy over dx. Over dx. Okay? It means what? Derivative of the first derivative. Dy over dx right here is y prime. So the derivative of dy over dx is derivative of y prime with respect to variable x. And this is the second derivative. So in short, people are going to write this way. D squared of y, you see? D squared, right, of y. And dx is dx squared. Okay? So how do we calculate this in terms of parametric? Same idea. We introduce the dt on both sides. On numerator and denominator. Okay? And this means what? You take the derivative of dy over dx with respect to t, and you divide it by dx with respect to t. Then you have derivative. Okay? So this is my dy over dx, right? The derivative of this is what? Let me rewrite in here so I have more room to write. Dy over dx is 1 over 2t minus 2, right? Let me write this way. 2 times t minus 1 raised to the negative 1 over 2. That's what it is. So the derivative of this, d of dy over dx, with respect to the variable t. This means what? I'm taking the derivative of this. It's going to be negative t minus 1 to the negative 2 and over 2. Yeah? And of course, dx over dt is calculated right here. So this one, which is negative of of t minus 1 raised to negative 2 over 2 and everything divided by dx over dt, so 2t minus 2. Okay? And if you simplify, it's going to be negative of t minus 1 to the negative 2 over 4 times t minus 1, or negative 1 over 4 times t minus 1 cubed, if you want to simplify. Okay? So, let's summarize what we're talking about in here. You have x as a function of t. You have y as another function of t. And you want to calculate, say, dy over dx, derivative y with respect to x. This is f variable t. This is y variable t. You want to calculate the ratio of changing of y over x. You can do is that dy over dt and then divided by dx over dt. Dy over dt is right here. Dx over dt right here. You have dy over dx by definition in count 1. This is the slope of the tangent line. Okay? And then second derivative, this is first derivative. The second derivative is what? Dy over dx, and take derivative over dx. Okay? Dy over dx, the first derivative. And you take the second derivative. And in short, people write this way: d square y over dx squared means second derivative. This is called Leibniz notation. Okay? And how do we calculate this? We still divide the top and the bottom by dx. So this is the same thing as d of dy over dx, right? Watch me. I divided by dt, divided by dt. And this notation on top means what? I'm taking the derivative of dy over dx. Taking the derivative of the first derivative with respect to t. And then this is dx over t, right there. And calculation I showed you right there, we have the answer. Okay? Okay, so make sure that you understand this. And what? Y triple prime is what? D of y double prime, okay? Over dx. Okay? And the double prime we calculate is right here. Instead of writing this way, what I wrote was what? D square of y over dx square over dx, okay? In terms of parametrics, and this is over dt, this is over dt. You calculate second derivative right here. You take the derivative of this one in terms of t, and then divide by dx over dt, which is right there. You got the third derivative. So forth and so on, with the fourth and fifth derivative. Okay. Now, we talk about our integral. In count 1, you have this. Integral of f of x dx, was that right? F of x is y equal to f of x. So let me write this way. I think it's clear. Y dx, run from a to b. Now change to t, this is what? Integral of y into t right here. It's a function of t. And what is dx? This is what? X prime of t dt. See, I'm using the chain rule. The derivative of x is the derivative of dx is what? The derivative of x is of t times dt. Okay? And now the variable going to be from, say, t equal to t1 all the way to t equal to t2. I'm not writing a to b anymore because a, b is, used to people think of x running from a to b, right? But now it's t, so let me emphasize this way. So in this example, for example, if 0 less than t less than or equal to 1, then t run from 0 to 1. And this one becomes what? Integral from 0 to 1. Y of t is right here, t plus 1. What is x prime t dt? X prime t is 2t minus 2, you see? X prime, 2t minus 2. And then dt. And you integrate this from 1 to 2. Okay? And this is what we learned in count 1, right? Integral f of x dx, y dx. Yeah. In terms of parametric, this is what we're talking about. Alright? So we can technically use parametric integral calculus for all the problems that we learned before. Okay, that's about the area. About arc length. That's one. Recall the arc length. ds is what? Square root of dx squared plus dy squared. It's come from this. you have a curve, right? Say from here to here, ds, I just draw it big. This is dy, this is ds, and this is the curve ds is very small. Pythagorean theorem walk you to here. And I can rewrite this way, square root of dx squared over dt squared plus dy squared over dt squared, everything times dt squared. It's the same, right? Multiply and divide by dt squared. And this is what? Dx over dt squared plus dy over dt squared under the radical and then times dt outside. See what it is? The derivative of the function x times t, the derivative of function y times t, take square root and make sure that you square up all the derivatives and then dt. Okay, so our arc-length formula that we learned before was what? Say what arc-length is integral of square root of 1 plus dy over dx squared dx, right? Or in general, we're integral of ds. That's what we wrote before. Now we convert to dt. This is what? Integral square root of dx over dt squared plus dy over dt squared dt. So our problem right here, if you want to calculate the arc-length when t runs from 0 to 1, the arc-length is what? Integral t run from 0 to 1 square root. What is dx over dt? Is 2t minus 2 squared. And dy over dt is 1. Right? 1 squared is still 1. And then dt. Right? Let me rewrite here just in case that people lost. Dx over dt is 2t minus 2. And then dy over dt is 1. Okay? And that will give you this formula right here will give you the equation for calculate the arc-length of the curve. This is the curve that I drawn before. T from 0 right here to 1 somewhere right there. Okay? That arc-length. This one. Of course, integrators. You have the integral for the measurement for the arc-length when t runs from 0 to 1. Okay? And of course, same thing for the surface area. Remember what we learned before? Say you have a curve and you are rotating about, say, the x-axis and the y-axis. Say rotating about the x-axis. Okay? And you want to calculate the surface area. The general formula that I gave you before was 2 pi r times ds, right? And r depends on you rotating about the x-axis. R here is y. You're rotating about the y-axis, and r is x. Or rotating any vertical or horizontal asymptote that you have to calculate on. But anyway, the formula is right here. So the surface area is integral of 2 pi r ds. And r here you have to calculate, and ds, what you have before, ds is square root of dx over dt squared plus dy over dt squared, and dt. Right? And plug in, you have the formula to calculate the arc-length, surface area. This is the one. It's just another way of looking at the problem using parametric, but it's all related to what we learned before. So I'll just give you the formula. All right. Let's move on to 10.3 and 10.4. We'll be talking about polar coordinates. And 10.4 polar coordinates. Okay, so far we use what's so-called the Cartesian coordinate or rectangular coordinate. We want to represent a point or a curve. We use two axes, the x-axis and the y-axis, right? The point right here is denoted by x, comma y, point P. And this is x, and this is y. For polar coordinate, we only need to use one axis, x-axis right here. So to indicate a point, we need two things: the distance to the origin and the angle make to the x-axis. Okay. So the point P right here is denoted by r comma theta, where r is the distance to the origin, the radius, and theta is the angle. Okay. So let's put it in there. But if you have a point P of 2 comma pi over 4, 2 means the radius 2, pi over 4 is the angle of 45 degrees. So it's going to be, okay, this is pi over 4, and this is 2 right here, right? This is how you plot a point. Okay. And at first we start with positive radius and positive angle, and later on you can have negative angles. Means we move what? Clockwise instead of counterclockwise. And then negative radius means what? The opposite of positive. But even though it's easier for many of us to use radius r as positive number. But if I have 2 pi over 4 is going to be right here, 2 pi over 4 in terms of polar coordinate. And if I want to do what? Negative 2 comma pi over 4, just flip it over. It's going to be right here, negative 2 comma pi over 4. Okay? And this point down here, gonna be 2 comma negative pi over 4. This angle from here to here is pi over 4. The angle from here to here is negative pi over 4. That's all it is about. Okay? So 10.3 is polar coordinates. Means what? We represent a point using two new components. The distance to the origin and the angle is made to the x-axis. Okay? So the main question on 10.3 is what? How do we convert back and forth between the rectangular coordinate xy and the polar coordinate r theta? All right, let me show you the formula to convert back and forth. First, we're going to convert from xy to r theta, and then I'll show you the other way. And now, this means what? You have a point. You know x and y. You know x, and you know y. Okay? You need to calculate r, and you need to calculate theta. And you know what? The picture right here shows you everything. This is x, this is y. The Pythagorean theorem say what? R squared is equal to x squared plus y squared. Okay, because this is the hypotenuse. So r is equal to square root of x squared plus y squared. And the angle theta is the angle in this right triangle. So I can use trigonometry right here. It's x right here, it's y right here, right? So this is x, this is y. So I can use tangent. We use sine or cosine, it's up to you. Tangent used to be able to do. Tangent is what? Opposite over adjacent. So y over x. So theta is arctangent of y over x. You have theta. Okay? The other way around. Say you have a point, r theta. You want to convert it back to xy. Okay. So graphically, this is what you have. You have a point P. And what you know is r and theta. You know this is the radius r. You know this is the angle theta. And what you want to calculate is x and y. Okay? Again, you're tricking here. You know the hypotenuse, right? I have a right triangle. So cosine of theta, cosine is adjacent over hypotenuse. So x over r. So excuse me. So I can calculate x. X is r cosine theta. Similarly, sine theta is opposite over hypotenuse. So y over r. So y is r sine theta. And that is how you convert back and forth. You know r, you know theta, you can calculate x, r cosine theta. You know r, you know theta, then r sine theta will give you y. You know x and y, then x squared plus y squared squared. You know r, you can calculate the angle theta by calculating tangent of theta, it's y over x, and then take the inverse of it, arctangent of y over x, you got the angle. Okay? And that is really the main thing for 10.3. As you see, I'm covering the full section in here, but not really long at all. Let me see if I miss anything. Oh, tangent. So you have a curve, an equation in terms of r and theta. Say, for example, polar coordinate. You have r equal to, say, pi over 6. Sorry, theta, angle, right? Theta, pi over 6. Guess what? this is really a straight line, right? X-axis right here. The constant is the angle, so the angle is always pi over 6. See what? Angle pi over 6. This is really an equation of a straight line in the polar coordinate. Okay? What if I give you this? R is equal to 2. Guess what? This is going to be a circle. You see why? Because the thing that changes is the radius, the angle theta. The radius is always 2. And this is going to be a circle. Circle, radius 2. Okay. And you're going to draw like a flower, like a cycloid.